Welcome everybody to this week's Ask an Astronomer episode. My name is Stefan. I'm from the Institute of Astronomy at the University of Cambridge, and today with me I have Kat again. You was here a few times, well, one time ago, and it's nice that you are here back again. Do you want to say again for our new viewers what you're working on and what's your interest?
Sure. Yeah. So I'm Katrina, and I am a second-year PhD.
Sorry, I think you have the stream open in the background and we hear the echo.
Sure. So I'm Katrina, and I am a second-year PhD.
Sorry, I think you have the stream open in the background and we hear the echo.
Sure. So I'm Katrina, and I am a
That's a weird effect. Sorry for the technical difficulties, we'll solve this in a second. Do you hear the stream?
Not anymore.
Okay. Sorry.
That was odd.
Let's wait for 5 seconds to see if it works, and then we'll continue. Okay, it seems to work. Go ahead.
Perfect. Okay, yeah. So I look at how planets' atmospheres evolve in the kind of early stages of their formation. So while you're building a planet, kind of how you can deliver stuff to your planet.
Yeah, and for those of you who are new here, we are just going to be here for about an hour and answer all the questions that you have. Just write them in the chat, so either on YouTube or on Periscope or on Twitch, or if you don't want to make an account, just go to slido.com and use the number the link in the YouTube description, or the number that's shown here on the screen, 74747, and then you can write us questions there on this web page. And actually, on our website, which is on the Institute website, we got a question that was sent to us before the show started, which was, which is greater, the difference in size between a single quark and the average human, or the difference between the size of the sun and the size of the observable universe? And do you want to answer this, Kat?
Sure. So this is a fun question. Firstly, we have to know what we mean by size. So do we mean how big something is in terms of length, or do we mean sort of how massive something is? So both a quark and the sun are small when you compare them to a human or the size of the universe. So if we make some estimates about the size of the universe, so the size of the observable universe, that's how much stuff we can see, we find that there's about 10 to the power of 20 times more stuff in the universe than there is in the sun. So that's a 1 with 20 zeros after it. Whereas if we look at, say, the size of a quark and the size of a human, we find there's actually something kind of similar in terms of the difference in size between the two, but the sun is just slightly heavier and more big in size compared to the observable universe than a quark is to the human body, if you take a typical just under 2 meter tall human. But yeah, that was a really cool question.
Yeah, and we also got a few questions on Slido, one of which was, what is dark energy and what does it do to us? And yeah, we also got this on YouTube. Thanks for the nice question. So dark energy is what makes the universe expand faster and faster. So the universe is expanding. It's doing so since the Big Bang, so since the beginning. That's actually really cool, but it's not even that surprising. So essentially, if you think about something that started with some kind of explosion, some kind of Big Bang, of course, the word explosion isn't really correct, but you can think of this, and it's just something, okay, it explodes, and then it grows and grows, so the universe expands. But the surprising thing that it's expanding accelerated, so it's expanding faster and faster. So usually it would just slow down the expansion, it would expand slower and slower, and eventually it would still continue expanding, but it wouldn't accelerate. But now with this dark energy, we don't know what it is or how exactly what causes it. We just noticed the universe is expanding faster and faster, which is why we call it dark energy. We have no idea what it is. Anyway, what does it do to us? So it would, if your body wouldn't be kind of holding you together, it would make you kind of expand by a really, really tiny amount. So like the expansion of the universe, it's really, really tiny on scales of like Earth-sized things. If the moon wouldn't be put together by the Earth, it would expand by 1 nanometer, I think per second, I'm not exactly sure, or per year, I think per second, due to the expansion of space. And you can imagine, like on a human scale, this is almost nothing. So dark energy doesn't do anything to you at all. Like it doesn't affect you in your normal life. But if maybe in a billion years you're interested on long time scales and you want to make it travel, let's say, to the Andromeda galaxy or to other galaxies that are further away, you have to take into account the expansion of the universe and also dark energy. There were quite a lot of questions on YouTube coming in. I don't know the ultramassive black hole in IC 1101 by heart, so I can look this up eventually, but I can't tell you right now. What is...
Yeah, so Peter had a question asking, energy can be converted into matter, so could dark energy be theoretically converted into dark matter?
Oh.
And so this, you might know more about this than me, but physicists, astronomers like to use the word dark just to mean things we don't know what they are. So dark matter is mass in the universe that we know should be there from the way other objects behave. So you can predict how mass will cause objects around it to accelerate. And so if we measure that acceleration, we should be then able to infer how much mass there is in sort of, say, the center of a galaxy. And what we find quite often with galaxies is that there is too much mass in the center of that galaxy to be accounted for by all the stars we can see. And so there's something there and it's massive and we can't see it, so we call it dark matter. But as Stephen's just explained with dark energy, that's energy that we don't know what it is or where it came from. So they're not really related to each other in any more than
that's exactly very good. It's a kind of thing of us naming things that makes it confusing, but it's actually not related. So we got a question on Periscope. Is it fair to say that dark energy is a result of negative pressure due to expansion of the universe? So that's a bit related to when physicists think about dark energy and what it could be. You would get the same effect as dark energy if you would have some hypothetical stuff, some fluid, that would have a negative pressure. And what is a negative pressure at all? Like, what's it supposed to mean? And essentially, I mean, that's not something in everyday life. It's more like a mathematical construct. But what I would do is make sure that you have some... if something is expanding, it would make sure it would be the same density. So imagine you have a volume of air with a certain density, and then you expand it to twice the volume, and it has still the same density. So there's more and more suddenly of it. That's kind of how dark energy works, and that's why people call it negative pressure. But it's kind of the same thing. It's not like one follows from the other. It's kind of, in the same area. What is the result when two white dwarfs merge? That's a good question. So I would suppose, I'm not sure if there's actually many observations of two white dwarfs merging, because I would assume that, actually you might know more about this than me, do you?
So I think there have been observations of one object that we think is the result of two merged white dwarfs. So a white dwarf is what a star like our sun will become at the end of its life. So once it's finished burning all of the hydrogen and helium it can, it's run out of fuel and it kind of collapses in on itself and becomes this very dense, very hot object, which is no longer burning fuel. So it's not shining in the way that our sun shines. Instead, it's just sort of very, very, very slowly cooling down. But because of sort of the fact that it results from the end of burning of fuel in a star, there's a sort of maximum size you would predict for a white dwarf. So they shouldn't really be any bigger than a certain size. But astronomers did find a while ago a sort of a too big white dwarf that shouldn't have existed. And so the theory is that that's what happens if you have two white dwarfs that are orbiting each other, and then they sort of get closer and closer together and eventually merge. So I think the answer is that you get a slightly bigger white dwarf.
Okay. So yeah, we got a few questions actually on Slido and YouTube about black holes and how we know black holes or how we know that they exist. There's the one nice thing, we have a photograph of the black hole. So this is the black hole in a really big galaxy, the galaxy Messier S87, which was taken by using many telescopes on Earth all together to kind of make one really well-resolved picture. And what you see there, this kind of dark-ish point in the middle, is a shadow of the black hole. So that's a point where there's very little light because most of the light kind of gets stopped by the black hole. And all the light around it is mostly from kind of the accretion, so stuff going on around the black hole. But in the center, this shadow is kind of the black hole itself. I mean, you can't really see a black hole kind of in the sense that you can see an everyday object because nothing comes out of it. So you can only see this shadow of the black hole. But that's how far we got. And it's also something that you would predict from kind of the theories of gravity that we had, like from Einstein's relativity theory. You would expect that there would be things like black holes. We got a question about what's the size and rate of the biggest meteor? Oh, that's...
Ooh.
I have no idea about this part.
Okay, so quick recap of what a meteor is and how it's different from a meteoroid and a meteorite, because they are very, very similar words that mean slightly different things. So there's a bunch of rocks in space. That's the starting point. When those rocks are relatively small and maybe might hit Earth, we call them meteoroids. So they're kind of junk in space. And if one of those happens to sort of head towards Earth and it enters our atmosphere, we might not really notice the air in our atmosphere, but when a rock is traveling very, very, very fast through our atmosphere, it gets heated up through friction. And so it becomes very hot, it starts to break up, it sort of heats up the air around it. And this creates what you might have seen if you've ever seen a shooting star. So a kind of a fireball through the sky. And that's what's called a meteor or a shooting star. And if that object survives, so if it doesn't completely burn up in our atmosphere, then when it hits the ground, it's called a meteorite. So they're really hard to find because Earth, it's covered in rocks anyway. And the bits that aren't covered in rocks are generally covered in sea. So we tend not to find most of the things that hit the Earth. So I think the largest meteorite that's ever been found was only a couple of meters across, but it's mainly made of metal, so it's really, really heavy. But I know the estimates for the one that maybe killed off the dinosaurs was more like tens of kilometers, maybe even 100 kilometers in size. And so ideally you don't want to find a big meteor because it means they can be quite dangerous. Yeah, so a couple of meters is the biggest one we know of. But
that's cool. Thanks. By the way, in case anyone, do you still see the screen? On my screen, it's a no connection error.
No, I can still see it.
Okay,
fine.
Great. We got a few questions about white holes. So maybe I should take a bit of a writer's sweep and explain a bit about what black holes are in particular, and then what's the difference and what are white holes. So when we have a lot of matter in one place, it creates a so-called black hole. And the reason for this is when a matter kind of curves space and time, and the reason why exactly it's not actually that important. The important part is that matter can attract light. So when you have a big clump of matter here and you have a photon going past this clump of matter, it will be kind of attracted, so it will be curved by it. And if this clump of matter is big enough, it can actually catch the photon, like the light, and it can't go out again. And that's kind of the definition of a big black hole. So a black hole is just something that's so heavy, so dense, that light cannot get out of it. And the special thing about black hole is not only light, but nothing can get out of it. So a black hole is just a thing where lots of stuff falls in and nothing comes out. And there's some funky space-time stuff going on around it. And the black holes exist. We saw them. We know how they get made. We know a lot about them. Then there's a hypothetical object, which we call white hole, which some people proposed could maybe exist, depending on certain conditions. And the idea of a white hole would be kind of the opposite of a black hole. So everything can get out, but nothing can get in. So a white hole would be something where lots of energy and matter is coming out of, and yeah, there's no way to get in. We didn't see any black holes, and we would expect them would be kind of bright, right? Because all stuff would get out of them. So at the moment, we are not very hopeful to find any, but it would be really interesting if we would. But at the moment, it's a very hypothetical thing. We got a question, what came before the Big Bang? So actually, I should say there's a kind of misconception in many kind of science articles, because sometimes scientists refer to the Big Bang as kind of the beginning of the universe, and some people say Big Bang to the time about 380,000 years after the beginning of the universe, where the universe kind of expanded a lot and cooled down, and the cosmic microwave background was emitted. So, of course, we know what happened before the cosmic... Well, we don't know exactly, but we're pretty sure we know what happened in the kind of first thousands of years after the beginning of the universe. Or the physics that happened there, we have some idea what happened. But we have no idea, and there's not really a way we can know at all what happened before the beginning of the universe, because all our physics only holds up to a certain point. We can't even get arbitrarily close to the beginning, because our physics doesn't hold anymore, because energy scales are so high, like we have no idea what physics we should apply there. So there's not really a sensible, a definite answer to what happens before the Big Bang. There are of course some theories like cyclic universes where universes collapse and then expand again and collapse, something like this, but that's all hypothetical at the moment. Also, we got a question, could life exist on exoplanet orbiting an O-type star? I have no idea about this. Do you know something about what is an O-type star?
Okay, so this is the astronomer's very, very logical classification of stars into O, B, A, G, F, G, K. We like letters. They don't necessarily make a whole lot of sense. So an O-type star is generally a very hot star, so it burns kind of white-blue color. So they tend to have surface temperatures that are kind of 3,000 or 30,000 degrees or more. So for context, our sun is about 5,000 degrees. So they're really, really, really hot. But that doesn't necessarily mean that they can't have sort of potentially habitable planets orbiting them. So we define something that we call the habitable zone around stars, and that's kind of the region of space around a star where liquid water could exist, because we think that that's what you need for life. And so depending on the mass and temperature of your star, that sort of region in space will move in and out. So in our solar system, it extends from kind of just inside where the Earth is to sort of slightly outside where the Earth is. So we're in the habitable zone, which is good for us. But around, for example, the TRAPPIST-1 system, which is an M-type star, so kind of the opposite direction, so a very red, quite small star, the habitable zone is much, much closer in, so it's much closer to the star. So I imagine for an O-type star, the habitable zone would be further out. But you could conceivably still have a planet where liquid water could exist, which we think is the kind of bare minimum for life.
Okay. You got a few questions about white dwarfs merging and white dwarfs merging with black holes. So that is like really hypothetical. We have no idea about what happens. And I'm not an expert at all on the like crazy general relativity phenomenon, so I can't really give you a comprehensive answer on these topics. I'm not at all confident in these topics. But when I have a black hole expert one day, I'll send them all these questions. We got a question on Slido about how long the sun has left before it burns out.
Do you want me to take this one?
I mean, if you want to.
Sure. Okay, so our sun is about halfway through its life. So we think it's about 4.5 billion years old. So it's been going for a while. And we reckon it has about 4.5 billion years left. And that's until it runs out of hydrogen. So our sun is turning hydrogen into helium in its core, and that's what creates sunlight and powers our sun. And so it's going to carry on burning hydrogen for another 4.5 billion years. And that's kind of dull. But then once it's done that, it's sort of once it's run out of hydrogen, it's going to become something called a red giant. So that means it's going to kind of expand outwards. It's going to become very, very red. And it's probably going to sort of eat Mercury and Venus, maybe even Earth. And it's going to become much more luminous. And then once it's a red giant, it starts burning helium in its core into carbon. So it kind of happily does that for a little while, sort of burning helium until eventually it runs out of helium. And then once it runs out of helium, it becomes very unstable. So it expands and contracts and expands and contracts, and its surface temperature changes wildly and its luminosity changes wildly. And it's sort of growing this denser and denser inner core of mainly carbon and sort of thin layers of helium and hydrogen around it. And that is actually very short compared to its, what we call its main sequence hydrogen burning lifetime. And sort of at the end of that very unstable phase, it's going to throw off all of its outer layers in what we call a planetary nebula. So you might have seen pretty pictures of sort of small central white dwarfs with layers of gas outside them. And that's the sort of final stages of a star like our sun. And what you're left behind with is a white dwarf, like we were talking about earlier. So a very dense, compact object that's very hot and is just slowly cooling down for probably the rest of the age of the universe. So I see someone's just asked, when will it become a red giant? So that will happen in about another 4.5 billion, about 5 billion years. So once stars spend most of their life on the main sequence, burning hydrogen even, and then all of the interesting stuff that happens after that happens relatively quickly in astronomical terms, so over millions of years rather than billions of years.
Yeah, so also we got this question while you were talking, how big is a star? So it apparently depends a lot on when you look at the star, and it can vary wildly between like really tiny, well, not tiny, but quite small, and as large as a solar system.
Yeah.
So we got one question about the Fermi Bubbles, and it's a long time since I heard about the Fermi Bubbles. I think that's a region around the our galactic center, where there's a lot of astroparticles coming from. So particles, cosmic rays coming from this region. So high energetic particles. And I'm not sure what's the most likely explanation. The last one I heard, which was about a year, I don't know, quite a while ago, was something about that maybe our galaxy had like an active core, and that had like jets that emitted lots of materials out of the galaxy, and this material kind of affected the gas, like ionized it or something, and this could cause all this radiation, like where the jets were. Like our galaxy isn't active anymore, but it could have been in the past, and these could have caused these two bubbles that are at the opposite sides of our galaxy to send all the radiation to us until today, like still. But I'm not sure of this. Like I'm not an expert in this field at all. But I think that's like one of the explanations at least. And what's the biggest star in the universe?
Ooh, let me see if I can remember.
I would suppose Betelgeuse would be a big guess for like the nearby universe.
So yeah, Betelgeuse is massive. I think there's one that's even bigger. It's got not a particularly exciting name. It's something Scooty.
Okay.
So but it's we call it a hypergiant because of names for big stars. So these are sort of very, very massive, very, very bright stars, and they tend to. So I guess to take a step back, it's actually quite hard to know how big a star is. When you look at them on the night sky, they pretty much just look like dots. So there's very few stars that you can directly look at and say it is so many solar radii in size. So it's quite possible that the biggest star in our universe we've not found yet. But I do know that this Scooty star is sort of 1,000 times the size of our sun.
Wow.
So it's really big.
So how big would this be in our solar system? Do you know?
Ooh, certainly. What's a solar radius?
Yeah. Okay. So yeah, I think it's like something substantial. Like I don't know, it would be close to some planets. But yeah, I think it was from Betelgeuse, but I'm not sure.
Okay, so 1 AU is 200 solar radii.
So AU is the distance between the Sun and the Earth, which is 200 times the radius of the Sun. So yeah, if it's 1,000 times as big as the Sun, then it as wide or as volume big or radius big?
Radius.
Okay, so then it would be far above the Earth and probably include Mars as well.
I think it would get all the way out to Jupiter.
Oh, Jupiter. Okay, there we go.
5 AU. So very, very big.
Okay, we got a Mond question. Finally, this is my first Mond question on the stream, I think. The question, or the comment, Mond explains galactic rotation curves way better than dark matter. Could you talk some about Mond? Okay, there we go. So the theory of gravity that we had a few hundred years ago, actually 100 years ago, was Newton's theory of gravity. That was quite simple. It just said the force thing, well, Newton's law of forces was just the force of something is, the acceleration something experiences is the force divided by its mass. And Einstein's theory made all this a bit more complicated, but this basic relation was kind of similar, at least on scales of the Earth. And what we found, actually I have a galaxy rotation curve, let me show this. When we looked at galaxies and looked at all the stars in galaxies and looked at how fast they're moving around the center, we noticed this doesn't make sense with all the masses in the galaxy. And either you would have to adjust our theory of gravity, and even like using Einstein's theory of gravity didn't work out here, so Newton didn't work anyway, and Einstein didn't work either. So the dashed line that you see on this plot, this is what we would have expected. And the main, let's say, mainstream argument is, okay, the galaxy is actually more massive than it looks like, and there's dark matter that we cannot see, like we did have no idea how it looks like, and it is just there and it's exactly distributed the way that it is to make this rotation curve work. And some people noted a bit of a problem that if dark matter is really the way we think it is, like cold and doesn't interact with anything, it's just completely boring, then it would kind of clump quite strongly in the center of this galaxy, and this rotation curve, so the velocities wouldn't work out exactly. And some people came up with an alternative theory of gravity. So they just took Newton's theory and added an extra parameter, and kind of ad hoc, I would say, to kind of fit this curve. But it turns out it fits really well, and it fits many galaxy rotation curves very, very well, and also explains a few other things. But on the downside, it doesn't explain many other things. So many cosmological things that happen on really large scales, like how does, like the Big Bang and the cosmic, well, the Big Bang it could probably, but the cosmic microwave background, so the image that we see from the Big Bang, and how structure forms in the universe. These are things that are really hard to explain with MOND. Actually, MOND, I should say, stands for Modified Newtonian Dynamics, so just a name for this gravity theory. And yeah, that's why it's not really widely acknowledged, because it seems to, well, it does explain a few things, but it doesn't explain, well, it doesn't explain everything, and Einstein's theory doesn't explain everything either, but it explains far more things, and you kind of can get these rotation curves to work with Einstein's theory if you assume some things. So that's why Einstein's theory is currently kind of the most prominent one and the most likely to be correct. And there was actually kind of a research paper out this week, I think, that gave a pretty strong argument for why various modified gravity theories cannot work for certain processes in the universe. So that argued against them being true. In case you are like interested in the details, you can look that up. I think it was, what was it, the title? I think David Spergel was one of the authors, but I don't exactly remember the title. But it should be this week on Archive. Okay, that was my Mon talk. Are you an astronomer? Yes, I would say I am an astronomer. Given, well, it depends on how what you call as astronomer, but I do study astronomy, and so I would say astronomer is a fitting title. I don't look through a telescope that often, so I'm not that on the practical side. I'm more of the kind of theoretical side, and try to simulate things and do things on the theoretical way. Oh dear, there we go. What's the most probable way the universe will die? We're getting in these sad topics again. Well, the universe will probably just expand, just continue expanding. That's the most probable way they would imagine now, is nothing spectacular will happen. It will just expand and cool down and kind of get more boring and boring until there's nothing interesting left. But there are many like exciting things that could happen, like there's some theories of like a big crunch that the universe will expand and eventually will collapse again, and other exciting theories, so I don't want to rule this out yet. What's the estimated size difference between giants like VY Canis Majoris and the earliest hydrogen plus hydrogen helium stars after the Dark Ages? Okay, so I don't know what these metallic giants are, so maybe I don't know if you know that, Kat. I know, yeah.
Yeah, so what we're talking about here is the idea that the very first stars, so when the universe was very, very young, it was made up pretty much of just hydrogen and a very small amount of helium. And so the very first stars that formed out of all of that gas can't have had any metals in them.
For the record, astronomers call metals everything that's heavier than helium. So everything from lithium is called a metal.
Yeah, we like to keep things simple. So the idea is that these very first stars that formed shouldn't have had any metals, so any elements heavier than helium in them really at all. Whereas when we look at all the stars we can see today, most of them look like they were born with some small amount of metals in them. So the question asks about VY Canis Majoris, which is a sort of very metal-rich red supergiant. So it's quite close to Earth, and it's about, I think, 20 solar masses. So it's about 20 times the mass of our sun. But I think, if I'm remembering correctly, that the kind of predicted mass for these population 3, we call them, so the very first stars, is sort of hundreds of times the mass of our sun. So they should have been really, really big. So bigger even than kind of the giant stars we see today.
Okay. I mean, of course, it's recently someone showed me like a plot of how big people estimated these first stars to be in respect to time, and it varies wildly. So there's a lot of uncertainty in these estimates, but
we've never seen. So
yeah, that's. I hope we will find some eventually. It would be really nice to see some of those. Well, okay, we won't be seeing any of these big stars because they would have died by now. But maybe, I don't know, see something like of a. Actually, maybe we could see them if they're like, I don't know, if we could see them like if they're really old and really far away, and well, not really old but far away. And anyway, it's complicated.
Old and far away.
So we got one question actually a while ago. We should maybe answer now. Could teleportation be made, and what do you think would be the best way to make it? So teleportation in the sense of you have some object or some information here, you click a button, and then it's somewhere else without any time delay. Well, at the moment we think it's not possible. So Einstein's theory of relativity tells us that you cannot transport anything, in particular no information, faster than the speed of light. So there's kind of no way to, well, at least no way that we know of that you could do this. There's something that's called quantum entanglement. So if you have two quantum particles, two really small particles, there are certain configurations when you can create two of these particles that are connected in some way, so they have a certain relation. Let's say the one is oscillating in the one direction, and the other one is oscillating in another direction. And what you know is they will always oscillate in opposite directions, but you don't know which one is oscillating what way before you measure them. And what happens is when you measure one of them, the other one also kind of becomes determined. And this is something you can measure, and you can notice that it doesn't seem to care about the speed of light limit. But also there are arguments about why this isn't actually information transferred, so that it still works with our theory. So that for teleportation, you would still need to kind of transfer the information of, well, who am I? What do I think? How do I look like? What am I made of? So currently, teleportation only with the speed of light limit. And how to make it? Probably some kind of scanning humans and scanning objects, let's say it this way, and printing them back out again on the other side. I think this is still a bit futuristic, though. Will anything survive the end of the universe? Depends on what you mean by survive, but I would say no. So there will be, so at the very end of the universe, like really far, far, far in the future, like billions of billions of billions, I don't know how many years, there will be just like, oh, actually, what will there be? Like the universe will be the same everywhere. So there will be some soup, and the whole universe will be filled with it, and everything will be the same. That's what we call. So there's a thing that we call entropy in the universe, which tells you essentially how not ordered something, or how unordered something is. So the more ordered something is, the lower entropy it has. And there's a kind of thermodynamics law that tells you essentially, in a nutshell, that entropy always has to increase in a closed system. And if you can apply this to the universe, which you can in some sense not, but let's just go with it, then the entropy will always increase, and eventually the universe will end up as an unordered mess, which is just kind of a soup that's the same everywhere. And then you can't have any kind of life. But don't worry, that's a far, far, far away, and I'm sure until then we will discover some new physics and discover that our theories are wrong, at least in some way, and maybe we'll be also wrong about this entropy thing. I have no idea about the Carina Nebula. Do you know about this particular one?
I'm just quickly Googling the Carina Nebula now.
Okay.
I'm afraid I don't know a whole lot about it. I know it looks very pretty through a telescope.
Okay.
Yeah, I'm afraid I can't say anything more about that. I wasn't aware it might be unstable, but.
I'll check this eventually. Sounds interesting.
Yeah. So, in general, when we talk about nebulas, we are talking about things we've seen on the sky that are diffuse and fuzzy, which leads to some confusion because it turns out that a star that's gone bang and thrown out a whole load of gas and dust quite close to us looks very much like a galaxy that's really, really far away when you're looking through a sort of early telescope. And so astronomers a while ago called a whole load of different things nebulas. And it turns out that quite often they are sort of completely separate classes of objects. So we have planetary nebulas, which is what you get when a star goes sort of through the final stages of its life and throws out a whole load of gas and dust around it. And we call that a planetary nebula. But we also refer to sort of nebulas in the sense of much, much more massive clouds of gas where stars are forming, which are obviously much, much bigger. They're just further away, so they look smaller when you look at them. So I think the Carina Nebula is a sort of second type of nebula. So it's a cloud of gas and dust sort of filled with stars.
Okay. We got one question from YouTube about the proton decay. So the question says that the proton, so okay, let me start with what is a proton. So all matter is made out of atoms, right? So everything, my hand, my glasses, my headphones, everything is made up of atoms. And these atoms consist of protons and neutrons. These are kind of two elementary particles, which themselves also consist of other smaller particles, the quarks, that we actually discussed at the very beginning of the episode for a short while. Well, their size. So that's kind of the smallest building blocks of matter. And there are some theories that predict that protons, so this one building block that many things are made out of, for example, hydrogen, would decay eventually. And these theories were quite popular a few tens of years ago, when we thought that would solve a lot of problems. But what we did is build huge detectors to search for protons decaying, and found out, well, there were no protons decaying at all. So those theories have been pretty much ruled out. And of course, you cannot rule out that a proton will ever decay. All you can do is take a lot of protons, wait a long time, and see did anyone decay. And if none decayed, you get a limit on this, on the lifetime of a proton. And as I guess from the question, the current limit on this lifetime is 10 to the 34 years or longer, and because we have not observed any decay, so we don't have a upper limit, we just have a lower limit. We just know either it doesn't decay or it takes really, really long to decay. And 10 to the 34 years is a really, really long time. Like, it's probably, what is it? A quintillion or something like this. So it's yeah, really, really large. And I suppose the kind of this end of the universe scenario, I don't know if I can compare these two times. I suppose the kind of end of the universe would, if the proton would decay, it necessarily would be after the proton that would decay, because as long as there's protons decaying, the universe hasn't ended properly. But yeah, probably protons won't decay anyway, so that's not really a problem. At least it's not a problem for us, because if they decay really, really slowly. You have a certain speed to escape gravity, but does it actually change gravity? So yeah, there's this thing called escape velocity, which is the velocity you need if you want to escape from some massive object. So let's say you're on Earth and playing, baseball or something, and you want to hit a ball as fast enough so it would fly out from the Earth and, go into orbit or something. You would have to make it go with the escape velocity, which is, I think, 11,000 something. Now I'm not sure what it was. Meters per second? Kilometers?
Kilometers per second.
Okay.
Yeah.
11,200 kilometers per second. With the small problem that your baseball would have friction, so it would actually be faster because it would get slowed down by the air. But that's kind of the basic idea. So yeah, that's a speed you need to escape from some astronomical body. And actually this is, yeah, so
it doesn't strictly change gravity, so gravity is the same. Yes. If by gravity what you mean is the sort of the feeling, the force you experience, what's sticking you to a chair right now, that's the gravity of the Earth where you are, and so that's not actually constant all around the Earth. So you can go to different places on the Earth, and gravity is just ever so slightly different. So if you took a set of scales with you and went all around the Earth and measured how much you weighed, you'd actually weigh different amounts in different places. So if you go up a tall mountain, you might weigh less. And so I think there's a follow-up question to this, which is if a massive object got close to the Earth, would gravity decrease because of the other object's gravity? And that's actually what happens to us every day when the moon goes around the Earth. So that's how we get tides, is the fact that when the moon is on one side of the Earth, there's the gravity you have from the Earth pulling the water down towards the Earth. But then you also have gravity acts everywhere. It just gets weaker as you go further away from the object. And so when you want to work out how much gravity there is at a certain point, you add up the contributions from all the other masses. In theory, all the other masses in the universe, but that's a lot of work. So we tend to just concentrate on the ones that are close by. And so on the Earth, you want to care probably about the gravity from the Earth itself, and then also maybe the sun and the moon. And so as those move around the Earth, the gravity on the surface of the Earth changes very, very slightly. So we don't notice when the moon goes round and around the Earth, and sometimes the moon is closer to us, so technically there's a small amount of gravity pulling us towards the moon, and so we weigh a tiny bit less. and we don't notice that at all. But when you have a big body of water that can kind of slosh about quite freely, the tiny difference in force from having the moon closer to a bit of that water and further away from another bit of that water pulls some of that water towards the moon, and that's how we get tides.
Yeah, that's
really cool.
That's actually also a really cool phenomenon of this is you just mentioned the gravity of the sun and the Earth. So there's a point between the Earth and the sun where both of those gravitational pulls exactly cancel out. Actually, there are a few of those points, and we call them Lagrange points. And that's really nice if you want to put a space telescope somewhere to put it on one of those points, because it need very little fuel to stay there, because, well, those gravitational pulls almost cancel, well, they do cancel out at some point. It just have to kind of stay close enough to this point. So that's what you can use. Yeah, also I think there's, like, what kind of scale would you need to measure this difference? Like, how big is the difference between my weight, let's say here, and on Mount Everest? Is it like something I can measure with a household scale?
Probably not with a household scale. It gets slightly complicated because the density of the Earth underneath your feet also affects experience.
So I have to take into account Mount Everest's own kind of mass as well.
Yeah. So you can get strange things called local gravitational anomalies, where it looks maybe like water is flowing uphill because your hill is sitting on top of a really dense sort of chunk of metal.
Okay.
Yeah.
That sounds really nice. I want to see this someday in real life. Okay, so you got questions about Hawking radiations a few times, so I suppose I should answer them eventually. Hawking radiation is something that happens mostly around black holes. So I talked a bit about black holes before. Essentially, these are these objects. Let me open a nice picture again, maybe a simulation this time. So yeah, black hole. Oops. Are these? Wait, that's the wrong picture. There we go. These objects where nothing escapes, right? Not even light escapes. There's a certain radius where there's an absolute boundary of. If you're within this radius, you can't get out anymore. So the explanation for Hawking radiation is slightly complicated, and there's like a kind of a simple version illustration that's also used by Stephen Hawking, I think, in his books. What was it? I think the first 3 minutes, something like this. And yes, I know the explanation is slightly wrong, so take this with a grain of salt. It's not exactly correct what I'm saying. But what you can imagine is that, what's true is that in a vacuum, or in general, everywhere, particles are constantly you get particles and antiparticles that get created and then annihilate again. What is allowing this is quantum physics and the Heisenberg's uncertainty principle. So you can kind of borrow a bit of energy from the universe, make a pair of particles, they annihilate again, and you give the energy back, and that's fine. So that happens all the time, everywhere. The funny thing now is, if it happens close to a black hole, you could imagine, okay, if there are 2 particles get created, one could fall into the black hole, and then the other, well, it doesn't have anything to annihilate again with, so you would just create particles of nothing. And that's kind of what happens around black holes. So around black holes, particles get created all the time, and they just kind of radiate away. So black holes have a certain temperature, you could say, so there's just radiation coming from black holes. And this is what we call Hawking radiation. And it makes black holes lose some of their energy. In particular, if your black hole is really small, this energy loss is actually really large. So if you would think about a black hole that could hypothetically, maybe, if it would be possible, created in a collider on Earth, like a really, really tiny black hole of a few, I don't know, maybe giga-electron volt, this would almost instantly evaporate because this energy loss from this Hawking radiation would just eat up the black hole. We call this evaporate. So yeah, that's how black holes lose energy, and this Hawking radiation, we didn't see it yet, so we didn't, because it's really weak, like it would be really hard to measure. But I think we are quite sure that it would exist, given that if our current theories of quantum physics and relativity are correct in that way. And yes, it's not exactly what happens, it's not really what happens, but that's kind of the best I can do without using math. And actually, I'm not that good at the math myself that I could do this live on. Actually, yeah. It's. I won't do math live on the stream. Okay. So there are new questions coming in. Could anti-gravity be created if it exists, and does it? Do you want to say something about anti-gravity?
Okay, so I've mainly come across this in science fiction, but from what I understand, it's sort of creating a space in which there is no gravity. And as far as we know, there's no physical way to get rid of gravity. It exists. There isn't a kind of a negative gravity that you can create to sort of balance it out. But what you can do is sort of oppose. So if you know what gravity is doing to you, you can sort of use other forces, so magnetic forces or a bunch of springs or rotation, to create an acceleration that sort of is equal and opposite to the gravity you would experience. So when they train astronauts for going up to the ISS and they put them in the planes that go up and down and up and down and up and down, what they're doing is they're creating a sort of a zero gravity environment or a very low gravity environment by essentially making the whole plane kind of fall freely towards the Earth for a little bit. And so while it's falling towards the Earth, the people inside the plane don't experience any gravity relative to the plane, so they float about inside the plane. And they are still experiencing gravity because they're falling towards the Earth, but it might not feel like it. So I think that's probably about as close as we get to anti-gravity. I guess another example would be kind of maglev trains that levitate using magnetic fields. So they're still experiencing gravity, but you oppose that gravity with a magnetic field, and so it looks like they're floating.
Okay. Yeah. So there's yeah, right. Okay, so we got a question about rotating black holes. Actually, so I'm not exactly sure what an ergosphere is. So if you want to clarify this, do you know what an ergosphere is? Or black hole? No. Okay. Anyway, so the question is about kind of rotating black holes, and actually, almost we think that most black holes, if not all black holes, are rotating at least a little bit, because, like, you know, a star like the sun is rotating, and this rotation is going somewhere. Like if the star ends up being a black hole, then there's still this rotation. Like the angular momentum is usually conserved. So you would just keep this this rotation, and most black holes would be rotating. By the way, the name for rotating black holes actually is Kerr black hole, who's a physicist who made like a lot of calculations regarding them. And they have some special features, like there's some asymmetry in the space-time around them, which makes like some sides brighter than the others. I think a part of this is what you can see in this picture, although I think the effect comes mostly from other relativistic effects. So yeah, you could see, I think, the effects of rotation on black holes, like from the picture. I'm not sure if this picture is accurate enough. And if you would want to make a more resolved picture, like with finer and smaller details, you would need a bigger telescope. And the problem is, with the Event Horizon telescope that made this picture, we already used all of Earth as a kind of a telescope. So for everything bigger, we would need to go to kind of space, and like building large telescope in space is really hard, or maybe on the moon, but then we don't have anything in between, so it's really hard actually to get bigger than Earth. Like building a telescope on Earth is much easier than building a telescope in space. So yeah, I think that would be quite a difficult question. And we got a new starter question. If you made two holes in fabric of space, say 1 light year apart, would it link the two places? Would you have created teleportation? Okay. So there's not a simple way of just make holes in space. I'm not sure if you could call a black hole actually a hole in space. It's rather like it's not really a hole. It's just kind of like imagine the Earth. It's just a kind of a point, or like a planet or something that's just pulling, like where stuff is orbiting around, and it's kind of pulling stuff in if it falls close to it. And a black hole is just, just imagine like a planet, just much heavier, or like a sun, much heavier. And then you have a black hole, but it's nothing like that. There's a hole in space or something. It's just, we just call it hole because it looks like a black circle, to be honest. So it's not like, hole is not really a good word, actually. Well, it's because stuff falls in there, but it just falls onto whatever is at the bottom of this object. It's not like there's something, a hole where something falls through and is gone or something. And well, now you're talking about kind of linking two places in 2 points in space-time to kind of create teleportation. So I think the idea that you might think about are what we call wormholes. So there is a theoretical, again, possibility that space-time could be warped in a special way, that 2 points are actually close to each other, unless you like want to go all the way around, like the normal way. And you could have a link between these 2 places. That would be a so-called wormhole. That would kind of be a shortcut through the universe. And we have no idea if they exist. It's like, again, very hypothetical. But if they would exist and we would have some way of going through them, which is not at all easy, like if you think about some weird tunnel through space-time, like it's not trivial how to fly a spaceship through this thing. But if it could be, then we could kind of create teleportation, I guess, in a way of you take a shortcut instead of going the long way around. So yeah, I think that would be an option. So did if I missed some questions, feel free to send them again. I'm trying to get all the questions that are sent, but I sometimes miss some of them. There was one, could the universe be a fractal? So a fractal is kind of a mathematical thing, right? It's kind of a definition of some sorts that give you an idea of an object that has, well, you could say a dimension that's not an even number. So there are some mathematical definitions you can use, and you can use them on the universe to find out, for example, on what scale the universe is homogeneous. So let me take a kind of a wider approach here. If you look at the universe on a small scale, let's start with small scales. You look at the solar system. It's very different from one place to the other, right? So where the sun is, the universe is quite hot. A few light years away, the universe is quite cold and empty. And if you look at the galaxy, then there are like spiral arms that are very full of matter and places in between where it's not so full. And if you look at even larger scale, you see large voids where there's almost nothing, and then big clusters where there's lots of galaxies. But at some point, if you zoom out enough, you will see that the universe looks kind of the same on every scale, everywhere. So when this is a simulation, what you see here on the kind of, screen, there we go. And what you see there is a distribution of matter. So kind of all these yellow points are big clusters of many, many galaxies, and these reddish parts are kind of also probably lots of stars and galaxies, and the black parts are voids where there's almost nothing. But if you kind of squint your eyes, it kind of looks the same everywhere. So on a really large scale, so this is billions of light years now, and then the universe more or less looks the same. And what people did is try to apply the concept of fractals and fractal dimension to the universe to figure out what's the size, like what's the scale I have to go to for the universe to look homogeneous. And that's kind of a number that's floating around a bit in some pages. I'm not actually sure what's the number. I think it's 200 megaparsecs, so like a few hundred light years, a few hundred million light years, but I'm not actually sure of the details. And that's kind of the way that you could say the universe is a fractal. But yeah, the universe itself is not really a fractal. It's more like the structure. If you look just at the structure of matter in the universe, that would kind of look like a fractal. I mean, this picture looks pretty much like a fractal. But the universe itself is just in quotation marks, a little bit curved sheet of space-time. Okay, let me check my paper sheet here of the questions that we might have lost. So what else do we have? Okay, so yeah, we got one question on our website as well about the Big Bang again. So sorry that I'm talking about all the time about the Big Bang questions. I suppose you don't want to answer the Big Bang questions today. The question was if isn't the Big Bang theory like a Ptolemy theory of epicycles? So actually, you might know that one. I heard of it in one of the astronomy classes I had at university. So the idea is, well, let me start with a historical idea. back in the days, eventually, people believed the Earth was the center of the universe and everything was going around to the Earth. And eventually they discovered how gravity works and noticed stuff goes kind of in certain mathematical ways. And they noticed it doesn't really match up with stuff going around the Earth, and actually it would match up much better with stuff going around the Sun. But they could also kind of fudge it and like add a few more equations and a few more rules to make stuff still go around the Earth and still make everything work. But it would get more and more complicated, and eventually you could just notice, oh, if I just set the Sun as the center of the solar system, everything works much simpler. And the question is the Big Bang a similar thing? So is the Big Bang also just an overcomplication, and isn't there a much simpler solution? And actually it's kind of the other way around. So the Big Bang is the simplest kind of explanation or solution to how the universe behaves that we have at the moment. So there are many, many more complicated ways of hypothesis of how the universe could be, but the Big Bang and the what we call a standard model of cosmology, so the lambda-CDM model, is the simplest thing that we have that describes everything that works. And we have not found anything. Well, we have found some minor problems, well, maybe some larger problems, but nothing that says, oh, this is of course wrong, and in particular, nothing else that's easy and explains those problems. So let me do a few final sentences. There's a thing that we call the H0 tension, which is a problem in cosmology where we notice, oh, something doesn't match up. If we measure the expansion speed of the universe today via different ways, we don't get the same result, and we should get, so something is wrong. But we didn't find anything that's also simple, a simple theory, or reasonably simple, and explains why these two observations don't match up. So for now, that's why we stick with the Big Bang model and our standard kind of cosmology. And yeah, I think that's it for today. So we have 6 p.m.'s universal time zone, or whatever time zone you're in. Thank you all for sending the questions, and thank you all for viewing, and thank you, Kat, for being here and answering all the questions that I have no idea about.
Thank you for having me.
If you want to see more astronomy stuff on this channel, there is a weekly live stream on Tuesdays that will tell you about some topic that you can check out. Otherwise, Monday again next week we'll be here again answering your questions, everything you want to know. Thank you all, and see you